Welcome back. I hope you have taken the notes from the board. Okay, now let me explain the typical doping concentration profile. Okay, now just now we got to know that this is what is your intrinsic semiconductor. This is what is pure silicon. I'm taking example of silicon and this is what is having N is equal to P is equal to Ni, which is 1.5 into 10 to the power of 10 per centimeter cube at room temperature. Let us say after doping, what do you mean doping? Let us say I am taking phosphorus. Therefore here I just already told you the silicon is sharing with 4 silicon atoms to get stability. Basically this is nothing but your covalent bonding, and this is what is the structure which you can observe throughout the material, and we have 5 into 10 to the power of 22 silicon atoms are there per centimeter cube, and out of these many silicon atoms per centimeter cube, remember this is per centimeter cube. If you have bigger volume, you will have more number of atoms in that given volume. Now in that per centimeter cube we have 1.5 into 10 to the power of 10 electrons, 1.5 into 10 to the power of 10 holes per centimeter cube. Then if I want to increase only electron concentration, that is what is called N-type doping, and if you want to increase only P-type doping concentration, that is what is called P-type doping. Now if you want to increase both of them, actually temperature, if you increase the temperature, both will be increasing. Why? If you increase the temperature, more number of bonds will be broken. If more number of bonds are broken, then obviously N is equal to P, which is nothing but Ni, that will increase. Now if I take phosphorus, what is phosphorus atomic number? 15. Then if you ask me electronic configuration, which is nothing but 1s2, 2s2, 2p6 and 3s2 and 3p3, where it has valency is equal to 5. When it has valency is equal to 5, then but if you dope with phosphorus, let us say, what is the doping profile now? If you ask me the doping profile, here the electron hole pair production due to temperature is nothing but 10 to the power of, for every 10 to the power of, in the order of 10 to the power 12 is to 1, for every 10 to the power 12 silicon atoms, one bond is broken. Similarly, if you ask me what is the doping profile, typically let us say 10 to the power of 8 is to 1. What does it mean? For every 10 to the power of 8 silicon atoms, one impurity atom will be added, right? Therefore this is nothing but doping. For every 10 to the power of 8 silicon atoms, one impurity atom will be added. It is in the order of 10 to the power of 8 to 10 to the power of 10. If I say that, then that is what your doping profile. Then if you add, then what we get? Let us say the silicon is replaced by phosphorus. This is what is our silicon. It is sharing with 4 silicon atoms, but it has valency is equal to 5, but shared with 4 silicon, one electron is extra. Then this is what, let us say I am explaining only like this is there, but if you see silicon, it is like one phosphorus atom for every 10 to the power of 8 silicon atoms. When I say 10 to the power of 8, I can say 10 crores of silicon atoms. For every 10 crores of silicon atoms, one impurity atom will be added. If one impurity atom is added, then that impurity atom is contributing extra electron. Therefore, how many impurity atoms you are adding, those many free electrons you are getting, and at room temperature the phosphorus atom is ready to lose that electron, and this valence electron from your phosphorus atom will take energy from external temperature or heat energy, then it will become a free electron. Therefore, then typically maybe at a time t is equal to 0, the moment when you add, already we have n is equal to what? 1.5 into 10 to the power of 10 per centimeter cube, right? And P is equal to 1.5 into 10 to the power of 10 per centimeter cube, right? Therefore, that is the n is equal to P is equal to, but you know how many we are adding for every 10 to the power of 8 silicon atoms, 1 impurity atom. Then if you calculate, that is nothing but your doping concentration. If you calculate, you will get the donor impurity concentration, because it is donating the free electron. Therefore, donor impurity concentration, if you calculate 10 to the power of 22 and then 10 to the power of 8, it will be in the order of 10 to the power of 14. I am just saying, giving one example, 10 to the power of 14 per centimeter cube. Means if you add 10 to the power of 10 to the power of 14 phosphorus atoms per centimeter cube, then it comes to 10 to the power of 8. For every 10 to the power of 8 silicon atoms, 1 impurity atom we are adding, because already we have 5 into 10 to the power of 22 silicon atoms per centimeter cube. In this, if you add 10 to the power of 14 impurity atoms, then if you distribute for every 10 to the power of 8 silicon atoms, 1 impurity atom will be added. Therefore, already per centimeter cube we have these many electrons, these many holes, but we are adding extra how many? 10 to the power of 14, and each phosphorus atom is contributing 1 electron. Therefore, I can say you will get plus 10 to the power of 14, and we are not seeing any holes because we are adding only impurity atoms, which each impurity atom is contributing 1 free electron. Therefore, if you ask me at a time t is equal to infinity under steady state, you know what will happen? There is something called law of mass action. There is something called law of mass action, where product of electron to hole concentration is constant, and that too n into p is equal to ni square. Now similarly, if you take here n, it is increased. Why electron concentration is increased? Because of doping and because of impurity atoms. But if electron concentration is increasing, then according to the formula or according to law of mass action, your n is increasing, then but ni is constant because temperature is constant. If temperature is constant, ni is constant. If ni is constant, ni square is constant. But ni is increasing because of doping. Then remember, your P will decrease. That is because as number of electrons are increasing, some of the electrons will recombine with the holes. What is hole? Vacant state. Some of the free electrons, due to excess number of electrons, some of the electrons will come and then recombine with the holes. Therefore, your hole concentration decreases. Okay. And let me tell you a point. You may say that maybe if I represent with the block diagram, right? Let us say we have some electrons. How many electrons are there? Let us say those many holes are there, but how many electrons? 1.5 into 10 to the power of 10 per centimeter cube, 1.5 into 10 to the power of 10 holes per centimeter cube. These many are there. Then let me tell you a point. After some time means, what does it mean? Each carrier, let us say this is one interested electron. After some time, this electron will be recombined with the hole. That is what is called lifetime. But let me tell you, if an electron is recombining with the hole, at the same time one more bond will be broken because temperature is continuous. When temperature is continuous, right, continuously thermal agitation of atoms will be there, and due to which if one electron in one hole, if that is what is disappeared, at the same time one more bond will be broken. This is what is called thermal equilibrium. At thermal equilibrium, if you see from outside how many electrons are there, those many holes, therefore that is what your intrinsic carrier concentration, but not the same electron will be there throughout the lifetime. What I mean, let us say this is the hole and an electron. After some time, right, due to collisions and all, the electron is coming back and then recombining with one of the holes. At the same time one more bond will be broken, then you will get one electron and then one hole. Therefore, that is what is called equilibrium state. Recombination, at the same time regeneration. Recombination is due to temperature, regeneration is due to temperature. Recombination is due to collision, that collision is due to temperature. Regeneration is due to atomic agitation or atomic vibration, that is due to temperature, and then bond will be broken, then you get regeneration. That is what it is, right? Therefore, what I want to say here, under steady state, because your electron concentration is increasing because of doping, then you see more number of collisions you see, then some of the electrons will be recombined with the holes, your hole concentration decreases. Then if you ask me what is your new electron concentration, your N dash will be approximately equal to, even though some of the electrons are decreasing, I think I can say it will not nullify completely the number of holes. Remember, because yes, it is trying to nullify, but because of thermal agitation, bonds are broken, definitely electron hole pair that will be there at room temperature, definitely holes will be there. Then what is that hole concentration or equilibrium hole concentration? That is what is explained by law of mass action. Therefore, when I say N is equal to this, some of the electrons will come and then recombine with the holes, your hole concentration will decrease, but your electron concentration will be approximately equal to 10 to the power 14, because 10 to the power 14 plus 10 to the power 10. I can say approximately 10 to the power 14, but some of the electrons from this portion is coming in and decreasing this part, but I can say N is approximately equal to your doping concentration. Let us say in this example, that is nothing but Nd, which is 10 to the power 14 per centimeter cube. We can ignore this part. Now if you ask me hole concentration, that is nothing but Ni square divided by your electron concentration, because N into P is equal to Ni square, that is nothing but N dash, which is basically Ni square divided by N dash is nothing but Nd. If you substitute the values, P dash will be equal to Ni square 2.25 into 10 to the power of 20 divided by 10 to the power of 14, you will be getting 2.25 into 10 to the power of 6 per centimeter cube. If you ask me how many holes are there under steady state at thermal equilibrium, 2.25 into 10 to the power 6, can I say 22.5 lakhs of holes, 22.5, let us say 22 lakhs of holes are there per centimeter cube. Very high or very low? 22.5 lakhs per centimeter cube. Remember, we need to compare with respect to electrons. How many electrons are there? 10 to the power of 14 per centimeter cube means 10 to the power of 7 into 10 to the power of 7. What is that? 1 crores of electrons are there per centimeter cube. With respect to 1 crores, how many crores you have? 0.2 crores. 1 crore versus 0.2. 1 crore versus 0.2. Unit is crores. Both of them are having common, which is nothing but crores per centimeter cube. Then that is why people call the hole concentration in N-type semiconductor. The hole concentration in N-type semiconductor is very less. Therefore, people call them as minority carrier concentration. Therefore, now your majority carriers are electrons. The same thing can be carry forward for the holes also, and you have minority carrier concentration holes. I am just representing because your hole concentration decreases. Therefore, tell me what is your majority carrier? Electron, minority carrier, hole. That is because of doping, and your hole concentration decreases from your intrinsic carrier concentration. That is because of recombination due to excess number of electrons, that is due to the doping. Here what I want to say, we are dealing with 10 to the power of 14, 10 to the power of 16, 10 to the power of 18. Therefore, now I can say this is nothing but your N-type semiconductor. Therefore, now this is nothing but your N-type semiconductor. With what? With the doping of 10 to the power of 14 per centimeter cube. Similarly, P-type semiconductor with 10 to the power of 14 acceptor impurities. I can say aluminum, where it is having valency is equal to 3. Then you will get P-type, N-type, then you combine P and then N, you get PN junction, you will get depletion region. Then if you ask me due to the depletion region, what is the contact potential, which is V0, that is nothing but V0 is equal to Vt ln Na into Nd divided by Na square, which we have seen before. And for a typical doping concentration, when I say typical doping concentration, that is nothing but 10 to the power of 8:1. That is what is our PN junction diode. Then for that PN junction diode, if you calculate V0, that is 0.7. Therefore, the amount of voltage what we need to apply externally to the PN junction diode to see significant current through PN junction diode is V gamma, that is 0.7. But I told you that V0 is depending on temperature and that V0 is depending on doping concentration. For a typical doping concentration, which is 10 to the power of 8:1, for every 10 to the power of 8 silicon atoms, one impurity atom is added. That is what is 0.7 volt. Therefore, if you take a PN junction diode, typical PN junction diode, then if you ask me, right, the doping concentration, it will be, therefore, typical doping, when you ask me typical doping, that is what is 10 to the power of 8:1 or 10 to the power of 9 or 10 to the power of 10:1. But if you take GNOR diode, what is GNOR diode? Heavily doped PN junction diode. What is GNOR diode? Heavily doped PN junction diode. Then if you ask me the doping concentration, that will be in the order of 10 to the power of 5:1. Your doping concentration is more. Due to which in reverse breakdown, instead of getting avalanche breakdown, you will get GNOR breakdown. Not going into the details. And if you still increase your doping concentration further, let us say that is nothing but your tunnel diode, then that is what people say 10 to the power 3:1, right? Then you will get some negative resistance region because of the doping concentration only. But what I want to say, the doping concentration is the one which is what is changing the characteristics of your PN junction diode. The doping concentration is very important. But when I say typical PN junction diode is nothing but typically doping concentration, and at room temperature the V gamma or the V0 will be equal to 0.7. I can stop here because I want to explain what is V0 and what is V gamma, and because in the BJT we'll have two PN junctions, two different V gammas or two different V0. That's why it is different, that is depending on doping, and then what is that doping, that is what I explained. Okay, done. You take this, then I'll go to PN junction diode VI characteristics. Okay. Over? Yeah. Now Now if you take a PN junction diode, in the voltage across the PN junction diode, now it is not internal voltage, this is what is the voltage what we are applying through external battery. Then there is a current through PN junction diode, and the relation between voltage to current is already derived. I am not deriving that part, you will get it from device operations. I is equal to I naught into e to the power of V divided by eta Vt minus 1. This is what is your exact current equation, which is what is describing the relation between voltage to current. What is A naught? A naught is nothing but reverse saturation current, I naught, where I naught, you can follow me, I naught is equal to reverse saturation current, that will be in the order of microampere or nanoampere in olden technologies, or discrete transistors, discrete PN junction diodes. And eta, V is nothing but voltage across the PN junction diode, and eta is nothing but statistical constant or empirical constant. That depends on again doping concentration typically. Therefore, if you ask me what is that eta is equal to 2 for silicon and 1 for germanium. But remember, not always 2, that depends on the doping concentration of your PN junction diode. Okay, then it can vary 1.32, 1.8 or 1.9 or 2. Therefore, for germanium it is slightly greater than 1, but you can say approximately equal to 1. Therefore, these are all approximately equal to the values. But in the examination, when you try to solve the problems in the examination, it will be specified explicitly the eta value. If nothing is specified, if that is silicon PN junction, you can take eta is equal to 2, and for a germanium eta is equal to 1 if nothing is specified. If that is specified in the problem statement, we can take it and then we can use it. And Vt is nothing but volt equivalent of temperature, which we had seen before, that is nothing but kT by Q, and 26 millivolt at room temperature. Okay, now if I plot the VI characteristics, this is V, the voltage across the PN junction diode, and then current. Therefore, here what is independent? Here this is independent. I told you, right? Indirectly we are characterizing your PN junction diode. How we characterized ideal voltage source, ideal current source, ideal resistor, etc. Now PN junction diode, but their voltage source, current source, resistor, straightforward to understand. Therefore, we got them easily. But here, getting the relation between voltage to current is not straightforward. For that, we need device physics, and we should know what is P-type, what is N-type, what is PN junction, what is cut-in voltage, what is contact potential, and what is diffusion current, what is drift current, and what is total current. If you incorporate all the concepts related to the PN junction diode, then we get the relation between voltage to current, which is nothing but I is equal to I naught into e to the power of V by eta Vt minus 1. And then all variables which are there in the expression or equation are described here. Now, if you ask me using this mathematical equation, then if you ask me the voltage to current, we can get it. But theoretically or qualitatively, I can say there is something called cut-in voltage, which I already told you. Till cut-in voltage, the current whatever you have or whatever you see through PN junction diode, that can be neglected. That is very small, because the depletion region whatever you have, that is what is acting as a barrier for your external battery. Until unless the external battery is overcoming the barrier which is present inside the PN junction diode, the majority carriers from N to P and then P to N cannot cross, then you will not see any current. Therefore, up to V gamma, we will not see any current. Maybe from V gamma, your current will be increasing, and that too it will increase exponentially. You can say this is what your V gamma, which is what is the voltage where you see the significant current. That is what is called forward bias voltage, when the voltage is greater than or equal to 0 and the current is significant, V, when V is greater than or equal to V gamma. Right? Now coming back to reverse bias, means when V is negative, then maybe from mathematical equation I can say that. Therefore, this is what, when V is positive, yes, fine. For smaller values of V, you can say current is almost zero, that you can substitute in the mathematical equation and you can get it also, or qualitatively up to V gamma. When V is significant and more than or equal to V gamma, your current is increasing exponentially. Coming back to reverse bias, right? What is that? When V is negative, e to the power of negative, that will be very small with respect to 1, that it can be neglected. Then you can get minus I naught, means it will be opposite to forward bias current, therefore your current will be negative, and that too, that will be almost equal to the reverse saturation current. That is what people say I naught. This is what is the voltage 0 function, and this is what is I naught. Then this is what is VI characteristics. This I naught will be, if you ask me, this will be in the order of, and this current will be in the order of milliampere. If this is in the order of milliampere, then you can take this will be in the order of microampere. And then V gamma, the typical value will be 0.7 volt. The typical value, not necessarily always 0.7. Okay. Therefore, this is what is your PN junction diode, VI characteristics. But every time if you want to represent your PN junction diode, something like this, it is difficult, and this is with respect to I is equal to I naught into e to the power V by eta Vt minus 1, and this is what people say exact equation, which is what is describing V to I. But people explain few more approximations related to diode, people call them as diode approximation 1, approximation 2 and approximation 3. Let's see what are those approximations, then when we use those approximations. Okay, take the graph. Can anyone tell what is the application of PN junction diode? The application of PN junction diode is switch. Maybe approximately, if the PN junction diode is in forward bias, then you can treat it as on switch. When the PN junction diode is in reverse bias, you can treat it as off switch. This is what is your forward bias, and this is what is reverse bias. You can neglect almost the reverse saturation current, you can take it as 0, therefore there is no current, open circuit. Forward bias, the significant current is there, then you can take it as almost short circuit. Therefore, when PN junction diode is in forward bias, on switch. When PN junction diode is in reverse bias, off switch. With respect to the bias voltage across PN junction diode, we can treat it as a switch. Okay. Now let's see the first approximation. When I say approximation, the name itself is saying it is approximation, it is not exact. This is what is your exact relation between voltage to current. Okay. Therefore, let me explain. Actually, I don't want to rub it, but okay, but I always try to compare with respect to exact relationship. Okay. Now, if I keep it as it is, let me draw a smaller graph. Therefore, if you take VI characteristics, which is nothing but up to V gamma, current is increasing, then it is almost 0. This is nothing but your I naught, and let us say this is your V gamma, which is 0.7. Now, the relationship between I2 is nothing but I is equal to I naught into e to the power of V by eta Vt minus 1. Let me take it is, okay. Now, when you say PN junction diode, first approximation, this is what is first approximation. For what is the first approximation? Listen, later on you can write down. First approximation means if you take PN junction diode, remember this is what your, for all the cases, this is what your PN junction diode reference, the voltage across PN junction diode is V and the current through PN junction diode is I. See, when I say forward bias, V is greater than 0, when I say reverse bias, V is less than 0, but you can represent it like forward bias voltage, but you can say positive voltage or negative voltage, that will define forward bias or reverse bias. And if V is positive, I is positive. If V is negative, I is negative. Instead of flowing current from P to N, if I is negative means it is flowing through N to P. Fine. Now, in the case of first approximation, right? Approximation, or people call this as ideal model. This is what people call it as ideal model or ideal PN junction diode, because in some of the problems it will be stated as consider PN junction diode as ideal. What does it mean? If the voltage across PN junction diode is greater than or equal to 0, which is nothing but positive, you take it as on. Therefore, case A, when voltage is greater than or equal to 0, when voltage is greater than or equal to 0, then you can take the PN junction diode as on switch. PN junction diode as on switch. Now case B, when V is less than 0, then you can take your PN junction diode as off switch. You can take it as off switch. Now then, yes, I think everybody will understand on switch short circuit, off switch open circuit. But if I try to plot the VI characteristics in first approximation or ideal model, what is that? If V is greater than or equal to 0, that is nothing but what? That is short circuit. Short circuit means what? Normally people represent the current like this. When V is less than 0, current is equal to 0. Can anyone tell the meaning of VI characteristics like this? I think this is fine. When V is less than 0, basically this is nothing but your reverse bias, right? And this is nothing but your forward bias. This is nothing but your forward bias, right? When PN junction diode is in reverse bias, your current is 0, straightforward. But when voltage is greater than or equal to 0, what is the meaning of this? What is current? Is your current infinity? Then what is the meaning of this? Normally people represent the current something like this. Therefore, is current infinity when the voltage is greater than or equal to 0. But remember, this is not exact curve. Is it matching to that curve? Approximately matching, right? But not exactly matching. It is approximately matching, but approximate, first approximation, or people call it as ideal diode or ideal model. But strictly speaking, that is what is the ideal model, sorry, exact model. Okay. Now, let me explain the meaning of the current when V is greater than or equal to 0 or when PN junction diode is on switch, okay, or short circuit. The meaning of this is nothing but, tell me what is, when PN junction diode is acting as a short circuit, what is voltage across short circuit? 0. Means the voltage across short circuit PN junction diode is 0. Then what is the current? Remember, the meaning of this is nothing but it can support any current from 0 to infinity. That depends on the external circuitry. Let me explain. Therefore, if you take a small network in the sense, let us say this is what is the battery. I don't know, am I visible? Okay, let me take, if you take the battery here, let us say this is 10 volt battery and this is what is the resistor. Let us say this is 1 ohm resistor. Then let us say this is what is your short circuit. Right? Tell me what is voltage across short circuit. Voltage across short circuit. This is nothing but voltage across short circuit is 0. Means there is no voltage drop across the short circuit. That is what is 0. Tell me what is the current which is what is flowing through this short circuit. The current which is what is flowing through the short circuit is nothing but that is dictated by the loop or the circuit what you have. You understand? Therefore, let us say according to this 10 volt and then 1 ampere. What is the current? 10 by 1. You will get 10 ampere. The same in series current is constant. Right? The same current is flowing through your short circuit even though the voltage across short circuit is 0. Now, let us say I am increasing the voltage. Let us say 10 is becoming 20 volt. When 10 is becoming 20 volt, tell me this is 1 ohm, 20 divided by 1 ohm, then your 10 ampere will become 20 ampere. When 10 ampere is becoming 20 ampere, then tell me in series your current is constant. Here also your 10 is becoming 20 ampere. But still, what is voltage drop across the short circuit? 0 only. Therefore, even though it is acting as a short circuit, even though the voltage across short circuit is 0, but the current which is what is flowing through the short circuit is depending on the circuitry where that short circuit is defined. Therefore, the current which is what is flowing through the circuit, the same current is flowing through the short circuit. What does it mean? even the voltage across the short circuit is 0, that is what we are representing when the PN junction diode is in forward bias, but it can support any current from 0 to infinity. That depends on the circuit which is what defined in the loop. I hope you understand this point. Therefore, what is the meaning of a parallel line which is on y-axis? That is nothing but it can support any current from 0 to infinity. That depends on the circuit parameters. That is what it is. I hope it is clear. Okay, but don't say that it is infinity. It can support any value. Basically, it has infinity solutions with one voltage. The voltage is 0, but it can support any current from 0 to infinity. Current wise, it has infinity solutions. Okay, that's fine. And maybe few people will have some confusion, because tell me if it is a resistor, right? Maybe I can clarify that. If you take a resistor, the same scenario I am explaining in a different way. This is example 1, now example 2. If I take example 2, right? Let us say there is a resistor, okay, and having value of R. Let us say I am applying the voltage V, and definitely there is a current I, right? There is a current I. Now tell me what is I according to Ohm's law? According to Ohm's law, I is equal to V divided by R, right? Now if I say this is short circuit, therefore when I say this is short circuit, what is the meaning of it? When I say this is short circuit means, what is your resistance value? Resistance value is 0, and we know that for short circuit, what is the voltage? The voltage is also 0. Then what is the current? If I ask for the current, using the same equation, current is equal to voltage is 0 and resistor is 0. Then what is 0 by 0? Right? This is according to Ohm's law. Therefore, if you take a resistor and voltage across the resistor is V, current through the resistor is I, then V and then I is equal to V by R. Now if you take a special case where R is equal to 0, because it is a short circuit, like your PN junction diode, right? Short circuit, but voltage across the short circuit is 0. Then what is I? I is equal to V by R. 0 by 0. Mathematically, don't take this, but I'm trying to apply to circuit. What is 0 by 0? What is 0 by 0? 0 by 0 is undefined. What do you mean by undefined? Are not applicable. Can anyone tell? What do you mean by 0 by 0? When we study in our intermediate, right, our lecturers used to say 0 by 0, undefined. We should not get that condition. If you get that condition, it is undefined. Let me explain. What is the meaning of that undefined? Then you'll understand. The same thing I can exploit to your PN junction diode also. Now, let me derive what is 0 by 0, right? Therefore, what is 0 by 0? 0 by 0. Let us say, let 0 by 0 is some value lambda. Then, what is the meaning of it? Can I write it as 0 is equal to 0 into lambda? Right? Tell me for lambda is equal to 1. This is true, right? 0 is equal to 0 into 1. 0. Therefore, 0. Satisfied, right? For lambda is equal to 10. 0 is equal to 0 into 10, which is 0. This is also true. Means when lambda is 10, lambda is 1, lambda is 2, lambda is 5, lambda is 10,000. For any value of lambda, this is true, means 0 by 0 is having infinity solutions. 0 by 0 can be anything, but we don't know what to pick up. We don't know what to pick up. Therefore, 0 by 0 is having infinity solutions. It is not defined. It is defined with multiple solutions. But we don't know what can be picked up from the infinity solutions. Therefore, that is what it is. Therefore, when I say 0 by 0 means the current can be anything, but the current is defined. The current can be anything. The current is defined. Even though resistance is 0, voltage is 0, but the current is defined with the external parameters which are there in the circuit. I hope everybody understood this point. Therefore, 0 by 0 is having infinity solutions. Then we don't know what to pick up, but the circuit is the one which is what. Therefore, similarly, for voltage 0, the current can be anything. That is the meaning of it. Take this. Then I'll go to second approximation. But remember, in the problems when we solve gate problems, are the problems from the workbook which we are going to see in the next session. Remember, almost in all the problems, saying that diode is ideal. When diode is ideal, what does it mean? If the voltage across the diode is greater than or equal to 0, take it as short circuit. If the voltage across the diode is less than 0, which is negative voltage, take it as open circuit. And then define current is equal to 0. Take this, then I'll explain second approximation and finally third approximation. Okay. I hope this is done. Now write down second approximation. See, as the approximation level is increasing, we will be going towards the exact relation. Okay, but this is ideal model. But we are expecting the diode to be like this, but practically will not have. Practically, that is what is the diode. Okay. Now, second approximation, little bit better than first approximation, and it will be somewhat close to your exact expression. This is what is level 2. When I say this is ideal, level 1 or first approximation, second approximation, little practical. Okay. Now, case A, again same thing. If the voltage across the PN junction diode, in this case people are incorporating the cut-in voltage, because we know that your PN junction diode is defined with cut-in voltage. If only the voltage across the PN junction diode is greater than or equal to V gamma, then only it is conducting, else it is not conducting, right? Therefore, if you ask me the PN junction diode, right, if the voltage across the PN junction diode, the reference symbol is this only always, then this is nothing but, this will be a battery of having the voltage which is V gamma. This is what people represent. Therefore, what is the meaning of representing with a battery which is V gamma is nothing but the voltage drop across PN junction diode. The PN junction diode will have a drop of V gamma, right? Means when you apply, when I say I am applying externally resistor in the battery, right, out of 10 volts, it needs some 0.7, it takes 0.7, remaining voltage will be given to a resistor, right? Therefore, it will have a drop of 0.7. It needs minimum voltage to have the conductivity between P to N and the N to P. Okay, you'll understand. I'll explain this part. Therefore, typically this is 0.7. Now case B, this is nothing but your forward bias. This is what people call it as forward bias. Here, this is what is forward bias, and this is what is reverse bias. Similarly, now when V is less than V gamma, if it is simply less than V gamma, you can take it as reverse bias. Then your PN junction diode, right? You can take it as absolutely open circuit. Therefore, what is the difference between first approximation to second approximation? Here we just took greater than or equal to 0, but here the V gamma is incorporated. Now, if you plot the characteristic, VI characteristic for the second approximation, right? Now, only when V less than V gamma, it is absolutely open, the current through open circuit will be 0. Therefore, less than V gamma, your current will be 0. Okay? Then more than V gamma, right? More than or equal to V gamma, what is the current? More than or equal to V gamma, that is nothing but having a drop, which is V gamma. But again, this is what is represented. Then what is the meaning of this? Remember, again, same as before. The voltage across your PN junction diode will be V gamma, but it can support any current from 0 to infinity. It can support any current from 0 to infinity. Even though it is acting as a battery of voltage V gamma, but it can support any current from 0 to infinity. That is true, right? We know that. Already explained ideal voltage source. What is ideal voltage source? Whatever may be the current which you draw from your voltage source, it has to have a voltage of the required voltage or defined voltage, whatever you are saying, right? It can support any current, but it has to have the voltage. Similarly, when you represent with a battery, right, it can support any current, but having the voltage drop of V gamma. That is what it is. Okay. Now, but this is somewhat close to our exact model. Okay. Now, people took third approximation. It will be little bit closer, or I can say this is what is practical model. I can say both second as well as third you can consider practical ideal model, practical diode model, but not completely practical, but close to the practical scenario or the exact scenario. Okay. Now, in this case, what is incorporated? I am saying that the voltage across PN junction diode is V gamma, but it can support any current, right? But to match to exact relationship, people took that the voltage across PN junction diode also will be increasing and current also will increase linearly after V gamma. That is what is incorporated. Therefore, when V is greater than or equal to V gamma, this is in forward bias. Therefore, if you ask me the PN junction diode will be equivalently represented as with some resistance. What is that resistance? That is what people call it as on resistance or forward resistance small rf. When I speak about resistance, we know that that is non-linear. If that is what is non-linear, then at what voltage? That depends on the voltage. Therefore, this is what people define the forward resistance or the forward dynamic resistance. I'll explain what is that forward dynamic resistance. Okay, but that is what is represented with the resistor, because it will have some drop. The voltage drop is not always now V gamma, not 0.7. It will increase like 0.7, 0.71, 0.72, 0.73. Therefore, as the voltage across PN junction node is increasing, current also will increase. Therefore, the drop across PN junction node is increasing. That drop will be represented with the RF, because as current is increasing, the voltage drop across RF will increase. So overall, if you ask me, the voltage across PN junction diode, that is also increasing more than V gamma. To represent the increment across PN junction diode, people added a resistor. Therefore, it will be close to the exact model. Now, reverse bias case, when V is less than V gamma, this is nothing but reverse bias. Then, if you take your PN junction diode, this is what is open. It is always open, neglecting the reverse saturation current. Now, considering, now if you draw the VI characteristics up to V gamma, current is not there, means less than V gamma it is absolutely open. Absolutely open. But from V gamma onwards, not only having V gamma, but it is having the increment The current increment as well as voltage increment means if this voltage is increasing, then your current also will increase. Okay. Therefore, here the slope of the curve is nothing but 1 by resistance. Why? Resistance is nothing but voltage by current. But this is y-axis, this is x-axis. Current by voltage is nothing but slope. Therefore, 1 by slope is nothing but resistance, or 1 by resistance is nothing but slope. That is what is RF. You take this now, then I'll explain what is RF. Okay. Maybe I can say this RF is the one which is what is, the third approximation is the one which is what is a little bit close to our exact relationship of V to I of PN junction diode. Okay. Take it. Now I'll explain RF. Then with this I can say, I think we have only up to third approximation, but until unless it is specified that the V gamma and the forward resistance of a PN junction diode, then typically we can go ahead with the first approximation to solve the problems. Okay. Maybe just to understand first approximation, second approximation, third approximation, I'll give you one common circuit. Let's apply first approximation for that circuit. For the same circuit, let's apply second approximation. For the same circuit, let's apply third approximation. Then we will see. Okay, then you'll understand very clearly. Then with this, I can say the PN junction diode is also over. But there is a technique or the methodology to be followed to solve the problems. Then if you apply that technique blindly, whatever may be the problem which is related to PN junction diode, we can solve very easily. Okay. That's what. Whatever theory we are understanding in the classroom, remember, when you solve the problems, then only you will understand whether you understood the theory perfectly or not. Because while solving the problem, we should apply the theory what we know. If you are not able to apply the theory in a proper way to solve the problems, even though you know the theory, it is not that we are not able to apply the theory to solve the problems. Then even though you know so much of theory, there is no use. Okay. After this, I'll explain the significance of the forward resistance, which is nothing but dynamic resistance. That's why represented with small letters. Okay. I'll explain what is that. Then we will see one common circuit or one example where I'll try to solve using first approximation, second approximation and third approximation. Then it will be so clear. Therefore, remember when I say a line which is parallel to y-axis, meaning of it is nothing but it's not infinity always, because normally if you take any impulse function, they represent like impulse where the amplitude is infinity but area under the impulse function is 1. But here remember, it's not impulse function. Normally impulse is represented with the arrow at very high magnitude, right? But it is not impulse, it is having multiple solutions for the same voltage. The current can be any value for a given voltage, right? That is what it is. See, this is also practical. This will also come under practical, but this is little bit close to the real scenario. You can call this as practical model. That is also kind of practical model. But instead of saying practical model, second approximation, third approximation. Okay, let me stop now. Maybe you can continue. Let's see the meaning of forward resistance in the next session. Okay, see you.